Last time we talked about liquid-fueled rockets, and today we're going to talk about a few more of the details. We're going to go into more depth into liquid-fueled rockets and basically what systems make them work. Recall that in a liquid-fueled rocket, you have liquid fuel and liquid oxidizer that get combined in a combustion chamber to make an exothermic chemical reaction, which results in super hot gas that is exhausted out of the nozzle, and that provides the thrust. The nozzle is super light, and so we need to keep it from melting. And so that's one of the key features also of this system. So there are lots of problems that we need to solve. So we need pumps to get the liquid oxygen and the liquid fuel into the combustion chamber. We need fuel injectors to mix the fuel and the oxidizer together as well as possible so we get a super clean burn. We need plumbing to cool the nozzle so it doesn't melt. So let's go through each of these things. How does a pump work? Turbo pumps are what are used in rocket engines, and they move the liquid fuel and the oxidizer to the combustion chamber. Those liquids must be super high pressure when they come into the combustion chamber, because if they aren't, what can happen is that you get the explosions in the combustion chamber, and if the fuel coming into the combustion chamber isn't super high pressure, then that combusted material could flow up your pipes. And that would be very, very, very bad because that would limit the amount of fuel coming in. So these turbo pumps have to be very, very powerful to get that fuel actually into the combustion chamber. And so we talk about turbine power in jet engines. And that is where combustion drives the turbines, which drives a shaft, which turns the fans or propellers in the inlet. But the main idea is that you have some combustion, which pushes the gas out, and it causes a shaft to turn. That's the key of the turbine power. We're going to use the exact same design. We're going to have a rocket turbo pump. So basically, fuel comes into a little combustion chamber. It causes a turbine to rotate, and that causes a shaft to rotate up here, which pumps more fuel actually into the system. So you have what's called a pre-burner combustion chamber, which combines the fuel and the oxidizer, like little offshoot of the fuel and the oxidizer, which drives a turbine, which drives the turbo pumps, which moves the liquids into the main combustion chamber. So how do you start this whole system? Well, it's sort of a self-sustaining system because you need those turbines to move fuel and oxidizer to go into the pre-burners, which turns the turbines, which cause the things to move. And you can't really do it otherwise. And so you need to have something to start the process. It's like a chicken and egg problem. And so if the turbines aren't powered, they can't run the turbo pumps, which can't bring fuel into the pre-burner. So you need an extra motor to start the whole thing up, just like you do in a jet engine. So the whole thing is super, super, super complicated. And if you look at a more detailed representation, you have even more stuff going on. And this is even a simplified, more detailed representation. Let's talk about fuel injectors versus carburetors. So what you really want to do is you want to take the fuel and the oxidizer, which are separate, and you need to mix them together, or else they won't burn cleanly. The worst thing that you could possibly get is liquid oxidizer and liquid fuel come together and then they stay separate from each other and they just pass out of the system without burning. So you want them to mix as well as they possibly can. You know, ideally you'd like them to be like molecularly close to each other. So in older cars, the way that this was done is they had carburetors. So a carburetor was a completely mechanical system, so you didn't need to have any computers or anything adjusting anything. And so they had floats and stuff like that that actually allowed fuel and air to mix together with different valves. and they are less efficient than fuel injectors. They needed to be warmed up. They got gummed up constantly. You had to clean out fuel injectors all of the time, but they worked pretty well. They mixed the fuel and the air together pretty well. And we didn't have computers back in the 60s and 70s to actually do this type of stuff. Any unburned fuel passed through the system into the muffler, which sometimes caused a backfire. So if you get a lot of fuel and air which move through the system into the muffler, you'd get combustion in the muffler. Fuel injectors, on the other hand, are electrically adjusted. So when the engine is cold and it needs a different fuel and oxygen ratio, it adjusts that automatically and it takes that into account. But it needs pumps, it needs a lot more electronics to actually control all of these things, so it's much more complicated. Let's look at fuel usage by a car, just so we can have some comparison. A fuel injector atomizes the fuel, which then is blown into the cylinder with some air, right? Cylinders in your car are very small. If you take a big truck gets something like 10 miles per gallon, let's say, which is 4.25 kilometers per liter. And if it's traveling at 100 kilometers per hour, which is roughly 60 miles per hour, it uses roughly 23.5 liters of gas per hour. So gas has a density of 0.75 kilograms per liter. So the truck uses about 17.6 kilograms per hour. You do all of that math and you calculate how much fuel is burned in each cylinder per second, and it comes out to about 0.61 grams of gas per second. That's roughly a paperclip. It's burning roughly a paperclip of gas per second in each cylinder. That's not very much gas. Cars are very, very, very fuel efficient. But if we look at the fuel usage by the space shuttle, on the other hand, there are some big differences here. It must overcome Earth's gravity well. Your car doesn't overcome Earth's gravity well. It must work in the vacuum of space. So it has to carry both the fuel and the oxidizer. It can't just take the oxygen from the atmosphere. It needs to carry both the fuel and the oxidizer. That means that the Space Shuttle main engine, one of the Space Shuttle main engine, uses 515 kilograms of fuel plus oxidizer per second in each engine. That is about 1,000 times bigger than the cylinder in a truck engine. So what that means is that the fuel injectors in the Space Shuttle main engines have to be very, very, very efficient and very, very, very big. So there are special fuel injectors for rocket engines. And it's basically like you have oxygen lines and fuel lines coming in close to each other, and they're what's called impinging on each other. And you have just a ton of these lines coming in, and they're causing lots of streams to impinge on each other. So basically what you're trying to do is take in a huge amount of fuel and you try to distribute it as much as you can through little holes as much as possible. And if you look at the Saturn V fuel injector, which was one of the biggest fuel injectors ever made, you could see lots and lots and lots of these little itty bitty holes where basically you have this fuel and this oxidizer all coming together to combine. And that's how you burn a huge amount of fuel every second. So you're probably aware the way that a car engine works is that you're combining fuel and oxygen together. You get an explosion, and that causes cylinders to crank up and down, which causes your tires to move and everything. Those explosions are heat. That heat gets absorbed into your engine, and your engine heats up very, very, very quickly. If you didn't have a cooling system, that engine would just break. It would run for a couple of minutes, the temperature would go up through the roof, and then it would crack open. And so you have liquid cooling going through your engine, which is taking the heat away from that engine and it's putting it into your radiator. And that is radiating that heat back to the environment. If the cooling stops working, the engine heats up very quickly, and then it causes the engine to crack, and it can break the engine, which means that your engine doesn't work anymore. A rocket engine is very, very, very similar. You're putting this fuel and oxygen actually into this combustion chamber, which is causing large explosions, which causes everything to heat up dramatically. So you really want to keep this whole thing from melting or cracking. So you can solve this using plumbing. So what you do is you run your extremely cold liquids around the nozzle in the combustion chamber before combustion. So basically you take the heat from the combustion chamber and the heat from the nozzle and you transfer that into the very, very, very cold liquid, and then you use that cold liquid in your combustion chamber. You take some of that heat away, which keeps everything nice and cool. There are other methods that you can basically keep the combustion chamber and the nozzle from not melting. And so you could put an ablative surface on the inside of the bell, something like ceramic or something like that. And that ceramic is slowly burning off, but it acts as an insulator. You can run the engines basically with a little extra oxidizer, so the exhaust is not as hot as it could be. So you basically run it with a fuel mixture which is a little bit off, so you don't optimize basically the exhaust to make it so it's not as hot as it could be, which keeps everything cool enough so it doesn't explode or doesn't melt. So this shows the RS-25 engine, which is what's going to be used on the SLS rocket. And you could see here all of this ice and everything basically falling off of the engines. You see all of this gas or all of this like vapor around the engine here, and that's all basically because it's very, very, very cold. You can see all this plumbing and everything has a lot of like ice buildup and everything on the outside because all of this stuff is so cold moving through the system. It's just causing a lot of water vapor to turn into ice and everything. And so we use that coldness of the fuels and of the oxidizer to keep everything nice and cold. In summary, turbopumps move fuel and oxidizer from the storage tanks to the combustion chamber as efficiently as possible. Those turbopumps are very similar to what are found in jet engines, and they cause huge high pressures to basically make it so that fuel and oxidizer, once it's combusted, doesn't go back up into the storage tanks, which would be very bad. So the turbopumps need to be very, very, very powerful. The fuel injectors mix the fuel and oxidizer as efficiently as possible. It's complicated because there's so much being mixed every second. So they have to be just massive. Then you have a plumbing system which pumps extremely cold liquids around the nozzle and around the combustion chamber, which keeps them nice and cool so they don't melt, because the things that are happening in the combustion chamber are very, 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 very hot. And that's very similar to an automobile engine.